So this is a video where I'm just going to go through the analysis of the mussel bed data that I uploaded for you. This is some data published by Peake and Quinn in 1993. And what they were looking at was the number of species and number of individuals, which is fairly self-explanatory, on an area of a mussel bed. So mussels are an intertidal mollusk. Lots of you have probably eaten them before, delicious with a nice white wine sauce. And we find them growing in the intertidal zone in vast, deep beds of these mussels where they filter feed when the tide is in. And then when the tide goes out, they're left exposed. The complexity of these mussel beds is a great habitat for lots of macroinvertebrates. So that's what we've got here in this column. There, in this column, we've got the mussel bed area. And here we've got the number of species of macroinvertebrates found, 3 species, 7 species, etc. And here we've got the number of individual macroinvertebrates found in each sampling area. So what we want to know then is there a relationship? Do we see more species as we get a larger mussel bed area? And where we see more species, do we then see more individuals? Or if we see more individuals, is it mainly more individuals of just one species? So it's not a very equitable distribution of this species richness. So first thing we want to do is have an eyeball of the data. We want to have a look on a scatter plot and see if anything's going on. Is there indeed any relationship between these two variables? And if there is a relationship there, what's it like? Is it linear? Is it curvy linear? Quadratic, cubic relationship, or no relationship whatsoever. I know my variables then, they're all quantitative, continuous variables, really. Yes, number of species is in this funny sort of count area, and number of individuals is a funny sort of count, but we're going to treat them both as quantitative continuous for C1 and quantitative interval for C2 and C3. But we're very aware with those that they are in this funny zone between counts and an interval variable. So we're going to need to be really careful on our assumptions of the regression. We're going to need to look at residuals and things like that. Okay, so first job, let's build a couple of scatter plots. Okay, we want to then put on the Y, we've got the number of species, the predictor is the mussel bed area, and we'll do the same for the number of individuals with the same predictor. I wonder what it looks like. Let's see. Come on, Minitab, no hurry. There we go. So we've got 2 plots have appeared. Look, mussel bed area, my predictor is on both x's. Number of species is on this y. Number of individuals is on that y. What I can see straight away, there's a very strong relationship between the two, isn't there? As mussel bed area increases, I can see the number of individuals increasing in a very linear fashion here, and then it all goes a bit wrong up here. Very strange. Mussel bed area is a predictor for number of species, a bit better. Nice linear relationship here, but you can see it's curving out. If I was to put a straight line through there, it's going to describe that spread of data very poorly. If I was to put a curvy line through there, that's going to be a bit better. So by eyeballing the data, I can see, yes, there is a relationship. I can think, well, is it reasonable to assume that the number of individuals of macroinvertebrates or the number of species of macroinvertebrates is in some way dependent on the mussel bed area? Or is this just a sort of correlation, causation, no causation type issue? Well, it's reasonable to make that assumption. I can think of a mechanism where the bigger the mussel bed area, the more individuals could be supported because of the complexity of this mussel, the substrate that the mussel beds give. And as we see more individuals, it's likely that we could see more species. So I think we're reasonable to progress with a regression here. So I will go into the regression menu, and I'm going to put in both my predictors, number of species and number of individuals. Sorry, both my responses, I beg your pardon. It's very early in the morning. Mussel bed area is my predictor. But because we know we've got this quadratic relationship, we've got a curve in the line. We need to put a curve in the line to better describe the data, to reduce down those residuals. Okay, remember this is sort of a least squares regression, so we want to get a line where we then square the error terms or the residuals, we minimize that squared error term. Okay, the reason we square the error term is because if we've got positive errors, which will be above the line, and then we get negative errors that are below the line. If we square a negative number, we get a positive. So the squaring is just to get rid of the negatives. So because I've got this curvy relationship, I need to go into model, and I need to then put in this quadratic term. So there we can see, look, muscle bed area times muscle bed area. In other words, muscle bed area squared. X, there's my x going into my y equals a plus bx. There's x there, and here's x squared. So I've got y equals a plus bx plus b2x squared, if you like. So I've got to put that quadratic term in there. If I wanted to put a cubic term in, then I would just drop that down to 3, and then I would have x cubed in there. Generally, we would be, if I saw a relationship where it was going up and then going back down again and then going back up again, then that would be a cubic regression. I haven't got that relationship, so I'll ignore that. So we will keep those two terms in there and store the residuals. Residuals, these very important diagnostic indicators, and I'll get this 4-in-1 graph of the residuals to have a look at those as well. Okay, I think that's everything. Let's see what we've got. Right, so there's the regression equation. Y equals, number of individuals y equals, there's the intercept minus 40.2. There's B, muscle bed, 0.1046 times the muscle bed area. And there's B2 with x squared there. The coefficients then are A, B, and B2 significantly different from 0. They're all there. There's the t-tests on those, as you've seen before. We can see that the intercept is not significantly different from 0. This is one of those situations where that doesn't matter too much. We're not going down, well, I suppose we would want to go down to, does no muscle bed area, where we've got a muscle bed area of 0, does that give us 0 species of macroinvertebrates, 0 individuals? Where that would imply that these macroinvertebrates were utterly dependent on the muscle bed, which may not be true. Sometimes we need the intercept to go through 0. This is one of those instances where we don't. However, what we do emphatically need is that B1 and B2 need to be significantly different from 0. Otherwise, we've got a flat line. And that flat line parallel to the x-axis is not describing any variability in y for variability in x. So we need both of those p-values here to be less than 0.05. This table looks a bit confusing, but it's just been compressed a little bit for some reason. So we've got the coefficient, the standard error, the coefficient, the t-value here. Normally we'd see the p-value here, but it's just dropped down there for some bizarre reason known only to Minitab. Same thing with the ANOVA table down here then. The whole regression, does that whole regression describe a significant amount of the variability? Yes, it does. Okay, muscle bed area squared, muscle bed area another on its own, and muscle bed area squared also are terms. These two terms here both describe a significant amount of the variability. That's giving me a R squared of 77.59. Look, okay, it's good. And then we've got all these diagnostics here. This is a very handy little Pareto chart, look, which is showing me if both of these bars here, both of these bars are representing the terms A and muscle bed area squared, and then muscle bed area squared times muscle bed area squared. This is getting confusing, isn't it? But we can see both of those terms, B and B squared, are both then describing a significant amount of the variability. We can see that from the ANOVA as well. From the residual point of view, the residuals are more or less close to the line. The residuals versus the fits, we can see there's a pattern going on here, which is a bit of a problem. This is because from what we could see in this scatter plot here then, look, the number of species starts to flare out as the muscle bed gets bigger. So some muscle beds have got more species, but some muscle beds, like this one, look, it's a bigger muscle bed, but it's got fewer species. So maybe that's a bit of an outlier there. This effect is much more apparent with the number of individuals. We're seeing, not always when you get a larger muscle bed are you getting more individuals. We've got this cluster of outliers here. Quite often see this in a plot like this. So there is the for number of species. Now we can do the same thing for number of individuals. In fact, we've been through number of individuals, haven't we? This is then going to be number of species versus mussel bed area, and we've got the same thing. Look, with R squared's a bit higher for number of species, but we've got a significant regression here. A, B, and B squared are all significantly different from 0, which is good. So we've described the data. Okay. Question is, could we do any better? At the moment, we're then saying we put this quadratic term in. So let's look at that plot on a fitted line plot. Let's look what that line would look like. Let's do it for number of species, mussel bed area there, and let's put the quadratic term in. And you can see, look, by that curvy line is describing it quite well, but we have got some larger residuals up here. This value especially is a bit of an outlier, but there's some quite larger residuals here. I think if there's another way to do this is to think, well, the data is sort of, perhaps this mussel bed area squared is behaving in a logarithmic fashion. So maybe if we then take the log to the 10 of the number of species, are we then going to get that line fitting better? Can we get a better fit? Can we get a higher R squared rather than by just putting a quadratic term into the regression? By taking the log 10 of the number of species, do we get a better fit of the data? Do we get a better regression model? And that would be shown most notably by a higher R squared. So what would that look like? If I go back to the fitted line plot, I'll go back to a linear regression, a straight line, but I'm going to take the log 10 of y. Let's put the confidence intervals on as well because they're pretty. There we go. Oh, that's not quite right, is it? No, I've done the wrong log 10. You can see I've bent the, I've taken the wrong log. So let's delete that. Go back to where we were. Options. I need to take the log 10 of x. Silly me. Better. Okay, so you can see now that R squared's gone up a little bit, not a lot, but it's gone up a little bit. We had 81 there. The R squared's now gone up to 83.8 there, so it is a slightly better regression by having this quadratic. By taking out the quadratic term and then taking the log 10 of the mussel bed area has given me a slightly better fit. If we do the same thing then, not for number of species, which was a slightly better fit to the data, but I'll do it for number of individuals. There, R squared is at 69.1%. Let's see what R squared was like when we take out the log 10 of x, and we go back to the quadratic term. We can see we've actually got a better fit for number of individuals with the quadratic term in, but for the number of species we had a better fit by taking the log 10 of x and keeping it as a linear regression. So we can start to see what we need to do to the data to get the best possible fit. So we could even come back here and think, well, what about then if I stick with number of species, I stick quadratic and take the log 10 of x, does it go up even higher? Chasing that really nice high R squared, 84.6, gone up a tiny bit more, look. So we're just trying to get the best possible fit of the data. By doing the transform and putting the bend in, we've got the best possible fit we can get for this data to try and explain what's going on. So in summary, we can say there is a non-linear relationship between mussel bed area and the number of species and the number of individuals. That non-linear relationship describes the best model we can build describes the log 10 of the mussel bed area is related in a non-linear fashion to the number of species, and the mussel bed area untransformed, we've got a model, the best possible fit of model we could get for how it's related to the number of individuals. We've got all these residuals here as well. Don't forget we need to check the assumptions of our regression is that we've got some no evidence of non-normal residuals. So let's just check those. And I've got both p-values for my Anderson-Darling test are above 0.05. Notice my sample size is still quite small, so I'm really very dependent on normality or no evidence of non-normality of my residuals. If this sample size starts shooting up a lot higher, if we're at the sort of 50, 60 sample size, then we can become far less dependent on these normality of these residuals. Indeed, we start to see even on in a big sample, you can start to see, because you've got so many points that are lying on the line, because you've got a good model, we start to see that this middle bar in the histogram starts going up higher and higher and higher. Looks a bit rude, doesn't it? But that starts to give us a leptokurtic distribution. This kurtosis starts to go right up because we've got so many residuals that are on very close to zero. In other words, they're so close to the regression line, their residual value is very small. And so as the sample size gets bigger, we get more of those, and that takes the distribution away from normality due to the high kurtosis, which there is not much that we can do about. So, hope that's useful. Another in-depth regression analysis. Hope you guys have had a play with the data that I uploaded last week, and hopefully you've done a similar analysis as well. If you've done some other things with the data, had a different play with it, come up with some other observations, then let me know. Be interested to see what you've done. Best wishes to all of you.